Welcome to this module on quantum error correction. In this video, we'll talk about how larger error correction code can help you correct more errors. As a reminder, we talk about quantum error correction because quantum states are inherently fragile, which means that small disturbances to the qubits may lead to errors in the quantum operations, and we need somehow to make a billion operations to implement the quantum algorithms that we care about. Quantum error correction is the means that we use to detect errors and correct them such that we can eliminate errors to get good enough gates to perform the cool algorithms. In the last module, we looked at an example of a error correction code, which is the Shor's error correction code, where we concatenated a bit flip code and a phase flip code to be able to detect both phase flip errors and bit flip errors. This is a distance-free code, as we discussed, which means it can detect one bit flip and phase flip error every time you try to measure the stabilizers. Generally speaking, making a larger error correction code is better. And the way we quantify that is using this distance d. And the formula that we use to say how many errors per cycle can we correct is written in this form. So you take your distance d, you subtract 1, and you divide by 2. And then if that's not a integer number, you round down. And that's the number of errors that you can correct per cycle of error correction. To make it slightly more tangible what this means in practice, we can consider a system where our physical qubits can do operations with a error rate epsilon phys, where error rate here means every time we do an operation, there will be a probability that there's an error, and that is the error per operation, which is our error rate. Similarly, we can define a logical error rate, that is the probability that there's a error on our logical qubit per logical operation. And it's described by this formula here, where you have some constant c times your physical error, now divided by something we call a threshold error, and then to the power of d plus 1 over 2. This threshold error is a very important concept in quantum error correction. And it generally depends on the code you're using, the way you decode your code, the type of errors that happens in real life, and actually many other things that are practical things in how you really implement your code on a quantum computer. The key thing you see from this formula is that if epsilon phys is smaller than your threshold error, then if you increase d, your distance, the logical error goes down. A plot of that is shown in this figure here that I've taken from the reference you see on the side, where on your x-axis we have our physical error rate, on the y-axis we have a logical error rate, and you see each line here is the simulation of what's called a surface code for different distances. And if we are on the physical error below the threshold error indicated by the dashed line, then if we increase the distance, you see this exponential suppression of the logical error. And that's what we are looking for. We want to be in this regime far below the threshold error in our operations, which means we really need to build very good hardware such that we are as far below this threshold error as possible. And then we can use quantum error correction to really push the error rate all the way down to the level we want it to be. Now, I said this was for a surface code, so let's explain what a surface code is. A surface code is a specific example of an error correction code where you take, if you want a distance d code, you make a two-dimensional grid of d times d qubits. On this grid of d times d qubits, we define stabilizers out of 4 qubits, either of the type ZZZZ or of the type XXXX. And the way these qubits go into it is that we make them out of squares on this 2D grid. So if you look at the blue square, we say this defines a X-type stabilizer by looking at the qubits in the corner of this X or this blue square, and take the X Pauli operator of those 4 qubits. We multiply them together. That's our first stabilizer. The next stabilizer, we go to the green square. In the green square, we again look at the 4 corners. We multiply the Z-type Pauli operator of those 4 qubits together, and that's our second stabilizer. And we so on and so forth throughout the whole grid. We need to take special care of the edges, where we also need to introduce some extra stabilizer. Those are only weight 2 stabilizer. So again, we make a smaller square here on the edge. It's a blue square, so we take the 2 qubits on the corner, take the X operator for those 2 qubits, we multiply them together, and that's another stabilizer of our code. And then what we do is we need to check whether an error occurred by measuring these stabilizers. We can measure, for example, the X-type stabilizer using the circuit here. So we take a Hadamard gate on all our data qubits. We perform a sequence of CNOT gates such that we do a bit flip on an auxiliary qubit, the blue qubit here, if the qubit are in the 0 state, otherwise in the 1 state. And the way we go through the circuit ends up being that the blue state flips to the 1 state if there was an error on any of these 4 data qubits. And similarly, we can do that for the Z-type of errors that you see in this circuit. And this is how we essentially run the surface code. We keep running these 2 checks all the time to check did an error occur. So with that, I would like to summarize what we learned in this video. We looked at the fact that larger codes are better, and we saw an example of a scalable code that we can really scale on a 2-dimensional grid to any large number of distance d. Making it larger, or making our codes larger, help if our physical errors are below the so-called threshold error. And in the surface code, this can be done, and we can go and make large-scale error correction codes with the surface code. More about that in the next video.